Okay, so this online lecture is meant to introduce you to the idea of work. And so far we've looked at this idea of just motion and how things have velocity and acceleration, how we can predict their motion. And then we looked at the idea of, okay, well, a force can cause an object to have an acceleration. But we never really looked at, okay, how does that force get exerted? And that is now we're going to kind of have our focus of this idea of work. How does one object exert a force on another object? How does that happen in terms of energy transfer? So work, by definition, is energy transfer from one object to another object via a force. So when one object does work on another object, it essentially gives that object energy or takes energy away from the object. Right? Our symbol for work is a capital W. Equations, there's actually two ways we can think about work. One is just kind of this idea of it's an energy transfer. So work is equal to a change in energy. E being kind of just the symbol for just energy. And the other way we can think about work is through the lens of force. And so work is F d cosine of theta. And let's kind of talk about what these things are. So F is the force that is doing the work. And we will look at just kind of the nuances of looking at the work done by a particular force versus the work being done by the net force acting on the system. D is the distance over which that force is being exerted. And theta, very similar to our torque equation, theta is going to be the angle between our force and our distance. And some of you may see just the similarity between the torque equation and the work equation. The torque equation was Fr sine of theta, and the work equation is Fd cosine theta. So it's different in terms of this trig function here, which produces a very different result. When you took the force, multiplying it by the r sine of theta term, that causes a rotation. Work, Fd cosine theta, which in math is called a dot product, this does not give you a vector. This does not give you anything with a direction. It just tells you how much energy is transferred. Okay? The units for force, there's two ways we can think about the units for force. If we think about just like the pure like FD, that's newtons times meters. Again, similar to torque. This newtons, though, is actually made up of kilograms, meters per second squared. So it could also be kilograms times meters squared per second squared. And didn't save enough room. This is also equal to a new unit called a joule, which we actually saw in the summer assignment. Okay, this is the idea of a joule. So this is rather abstract right now, like what does this even mean? So I want to just jump right into an example to hopefully make it a bit more concrete, this idea of like work being done by a force. So you have this example in your workbook that says, find the net work done on the box. So I've already done like the legwork for you. I've given you a box. It has this pulling force of 100 newtons at this angle of 30 degrees. It has a normal force. It has a force of friction. It has a force of gravity. And this thing is being pulled a distance of 5 meters. So we're just going to apply our work equation to all of these different forces. So our work equation is work is equal to Fd cosine of theta. And we're just going to figure out, well, what is the work done by each of these individual forces, and then what is the total work or the net work done on this box. So if I think just about my pull, this is work done by my pull. Is going to be like the force of my pull times the distance times the cosine of the angle that's in between my force and my distance here. So if I just plug some values in, This is going to be 100, because that's my force. The distance this object moves is 5 meters, so it's going to be times 5. And then the angle between this force and this distance is 30 degrees. So 100 times 5 times cosine of 30. And hopefully you pause the video, get out your handy dandy calculators, and calculate it out. I'll look at my notes here. I have that it's equal to 433.01 joules, capital J for the symbol. Okay, so this pull is giving the box 433 joules of energy. Okay? It's what's causing it to move. So let's kind of continue on and look at what's the work done by the normal force. So this would be the work done by the normal force would be equal to Fn times d times the cosine of that angle. Okay? My normal force is 97. My d value is 5. And then my angle, look here, my normal force is up, my distance is like to the right, so this is actually a 90-degree angle. So this is cosine of 90. And cosine of 90 is 0. So the work done by my normal force is 0. My normal force is not helping the box move forward. It's contributing 0 joules of work in that sense. Okay, let's continue. Friction. So work done by friction, this is going to be my force of friction times distance times cosine of theta. Force of friction is 20. Distance is still 5. Cosine of, okay, let's look at this angle here. I'm going to erase this guy here. My friction is going to the left. My distance is to the right. So like this whole thing is 180. So it's going to be cosine of 180. Cosine of 180 is -1. So this tells me that the work done by my friction is equal to -100 joules. Okay, friction is doing negative work on this thing. This box is moving to the right, and friction is not helping it move to the right. In fact, friction is actually hindering it from moving to the right. So that is why it contributes negative joules. Like that's taking away energy from the box. Okay, last force, this is the force done by gravity, or the work done by gravity. So hopefully you kind of see the pattern here. The work done by gravity is going to be the force of gravity times distance times cosine of theta. My force of gravity is 147. My distance is 5. My angle is, it's 90 again. See, my gravity is straight down. My distance is to the right, so that angle is 90. And cosine of 90 is 0. So the work done by gravity is also 0. Very similar conceptually to the normal force. My force of gravity is not helping this thing move forward. So it's contributing 0 joules of work to getting this thing to move forward. So now when I think about like my total work, I have my 433 plus 0 minus 100 plus 0 is 333.01 joules of work. So that's the total work being done on my box. Okay. So kind of in summary, friction, like the definition of friction is the force that hinders motion. So friction is going to always contribute negative joules. Okay? It's always going to take energy away from your system. But normal force and gravity, these are not always going to be 0. It really just depends on the situation. So for example, I've got this marker on my hand. My hand is exerting a normal force on this thing. And if I move this up, well, definitely, like the reason my marker is from like here to here is the fact that my hand, my normal force on this, is doing work on my pen. Okay, so in that case, my normal force is up, my distance it moves is up, so that angle is 0. So I'd have a positive work value for my normal force. FG can definitely do work on an object. So like if I were to just drop this, the FG is down, the distance it moves is down, so the FG would be giving a positive work value to my marker. Okay. So these are examples of when you have a constant force that is being exerted and causing your object to move. We definitely have cases where the force is a non-constant value, and that's a little bit harder to analyze, but we can analyze it in terms of a graphical analysis, looking at a force distance graph. So the best way to kind of show you that is I'm going to do a screencast on the board here. So the video is going to shift to a screencast that looks at the graphical analysis of work being done by a varying force.
Okay, so when work is done by a varying force, it's a little trickier to figure out the work done just using the FD cosine theta equation, but we can look at it graphically. So for a force distance graph, the area under the curve is equal to the work done. So this first graph here shows a constant force. And so that's pretty straightforward. We know that just work is equal to F d cosine of theta. And if it's a constant force, then this y value stays the same. And it goes from a particular, 0 to x distance, so that's a d. And that kind of makes sense. The area here is just equal to the force, the constant force, times the distance over which that force was exerted, and this would be a cosine of a 90, okay? So mathematically, we can kind of see in situation 1, where if I have a constant force, the equation works out. Now, in the situation of equation 2, this is an example of like a spring force doing some work, and in that case, you have to almost look at the average force that is being utilized to do the work. But again, if we just look at the area, so work is just the area under the curve. In this case, it is just a triangle, like this area down here, and so we would just say that's just equal to 1/2 my height, which is my force, times my distance. And in this case, the force, if it's a spring force, that spring force is equal to kx, and that's where they get that 1/2 kx squared value. Okay. Now, in the case of where you have like a continually changing force, then you have to actually use calculus. And so in this case, work is still the area under the curve, but in calculus, we know that it would be equal to the integral of, integral of the force function. And we will not go into that depth of mathematical knowledge, but just kind of, you need to understand the basic idea that if you have a force distance graph, that the area under the force curve is equal to the work done.